Well, good afternoon to everyone. My name is Miguel de Mayuga. I work for Earthlink.
My name is Dan Golding. I work for NetRail.
What we're going to present to you today is something on our experience setting up Confederations for initially the MindSpring network, now currently the Earthlink network, and
soon to be the NetRail network. But let me give you guys a little background on who we are and where we are and what we've done. Basically, quite a while ago now, we both used to work for the old MindSpring before it got bought out by Earthlink, and our boss came into us one day and said, well, how are you guys doing redesigning the BGP architecture on the network? And we couldn't give him a good answer because we really hadn't thought about it. So we had to come up with a cool, reasonable, sensible, scalable way to redesign our network architecture. Now, the advantage that we had at that time was that we weren't in a situation where we had lots and lots of legacy customers. We had millions of dial-up customers. So we had an unusual degree of latitude in redesigning our network and making it as cool and as resilient, as survivable, as scalable as possible. So we looked at a number of different options. We looked at route reflectors for a while. We looked at an iBGP mesh for a while. For a long time, we were in isolated eBGP. But we finally settled on a confederation approach. Basically, there's a couple ways of doing your network architecture. You know, there's kind of an older way and there's a newer way. Now, the older way, is more classically of a time when things like ATM, were big. And ATM, of course, is still big in our networks. It's in all of our networks. But ATM's time is kind of coming to pass. As we move into the future, what we're looking at now is packet over SONET. We're looking at lighting up huge fiber ring networks, packet over SONET. ATM is moving out to the edge, becoming aggregation technology. So a lot of the old ways of doing things, the conventional network architectures, the full mesh iBGP, the fully meshed network via ATM PVCs, that stuff is moving away. That stuff is receding into the past. So. Here's what we didn't like when we looked at some of the more conventional ways of doing business. We feel that it's not adapted to the sort of SONET optical ring networks that we were looking at. Packet over SONET is the big technology. We're all making that jump. ATM out, packet over SONET in. There's an issue of fragility. Basically, we felt the older ways, some of the route reflector architecture, certainly the full mesh iBGP, were far more fragile than some of the stuff we were looking at. Finally, some of the old ways of doing things were prone to user error. In today's kind of internet environment, we felt we needed something that was much more resilient, where you couldn't bring down the customer by a typo, where a fiber cut wasn't going to cause a major network outage. So the way we looked at, we had a couple preconditions. We had a couple criteria when we sort of did this network approach. Can you go back one? The first thing is we wanted to emphasize large-scale IP-based fiber ring networks, where there's no IPX going on here, there's no SNA, none of that weird stuff. This was going to be big. We weren't going to start it small and scale up. We knew it was going to be big from the beginning, so we kind of skipped some steps. We knew it was going to be based on a fiber ring. That's kind of a big thing. We knew that probably the lease line point-to-point, OC3s, DS3s were not going to do it, that we were going to be doing what everyone else here is doing, lighting up lambdas, lighting up dark fiber. Also, in the NetRail portion of this at least, our main customer are service providers, so we had to kind of optimize this for the needs of service providers. And the big other things we wanted to get out of this were great fault tolerance. In other words, we wanted good failure modes. Anyone can design a network that's going to operate great when every piece of equipment in the network and every strand of fiber is operating at top efficiency. What we wanted to do was provide good failure modes so that when the failures that we knew were going to happened, we'd still be okay, that our customers would still get the service they were paying us for and the service they deserved. The other thing we wanted out of this was some usable traffic engineering. MPLS is all well and good, but MPLS is not quite out of the oven yet. We needed something that could give us some basic traffic engineering abilities without MPLS. We decided to do two things to get to this end. A very, very strong community structure and the use of BGP confederations. Now, One thing we looked at, of course, briefly and of course rejected, was a full IBGP mesh. Now the problem here, and I'll just review this, I'm sure a lot of you guys know what's wrong with the full IBGP mesh, but I'll go through the whole mental exercise. Is of course when you have two routers in your network, two BGP speakers, an IBGP mesh works great. 3, it still kind of works okay. When you get to 4, 5, 6, 20, 60, or 100, adding a new BGP speaking router to the network becomes a major exercise. And if you miss one, you've got suboptimal routing. So what's going on here? Every router in full mesh IBGP must be meshed with every other BGP speaking router. Works well in small systems, but the number of links grows exponentially. Eventually you consume all CPU, all memory, and all of your engineering resources just keeping up with this. The other alternative, and the alternative in use probably in many of the networks around here, is route reflectors. Now, route reflectors is fine architecture, particularly if you have a full mesh ATM topology, a star network. Works very nicely, because if you think about how route reflectors work, you're presupposing a star system. You're presupposing having a route reflector server, like these guys, and accompanying route reflector clients, like these guys. The problem is, we're building a ring here. We're not building a star. And even, frankly, even when you had ATM PVCs, they weren't physical. So, ATM redirects and stuff all aside. So basically, we looked at it and said, okay, what happens if we blow up that piece of fiber there and we blow up this piece of fiber here? Well, the problem you can get is you can have route reflector clients that get isolated. In other words, this guy has a path to a peer, but he's not getting any routes from the route reflector server. So we felt this wasn't sufficiently survivable in a fiber ring network, so we wanted to look a little bit elsewhere. The final thing we didn't like about some of the conventional ways we had done things, and some of the conventional ways we saw other people doing things, was filtering. We did not like the fact that lists of IP prefixes and AS numbers had to be set on border routers. That really bothered us. We felt that did not scale in any way. It worked very well when most customers were single-homed. And you look, historically, say 3 or 4 years ago, and how many of your customers were really running BGP with you. And then look at the data today. The percentage of customers running BGP with most internet service providers has skyrocketed. And why does this come about? Because of e-commerce. Because in the old days, internet access was a luxury. Then it was kind of sort of a nice thing, like 11 by 17 paper in the copier. But now it's a business necessity. You can't do without it, so everyone needs a backup connection. You need a backup connection, you need BGP. And when you start getting a huge number of BGP sessions to turn up, having static filter lists and AS path lists on your border routers just isn't very advantageous. The changes are very manpower intensive and certainly prone to error. So we decided to go with BGP confederations. Basically, the system we designed was that each POP, and of course these aren't necessarily just really one router, but each one of these represents a POP. Each POP is going to peer with each other POP. Every POP becomes a confederation sub-AS of its own. The advantages here are that the routers only peer with their neighbors, highly survivable. You get a fiber cut here, it doesn't matter. Essentially you have reroute capability. If you have a path to get to peering, or if you have a path to get to transit, your data is going to get to peering or transit. It's very scalable, almost infinitely scalable. The only limitation is, of course, the number of private AS numbers, which by RFC is set at 1,000. It's easily configured. If you want to put a new router in, you don't have to put in the configuration information for all of your other IBGP peers. There's not a complex route reflector setup. All you have to do is say, for this guy, I'm going to put in this guy is his neighbor and this guy is his neighbor. And this guy doesn't have to worry about all these other routers, only his neighbors. Also aids troubleshooting. The big advantage there is, this may sound pretty trite, but if you do a show IP BGP on a Cisco or a show route on a Juniper, one advantage of this confederation approach is you can see all of the POPs that a route had to pass through before getting to the point where you're looking at it. So that was a huge advantage.
In other words, you don't have to find out, or memorize the loopback addresses.
Right.
Each router within the POP,
Right.
the POP will be identified by the Confederation AS number. And
Right.
It will show up in your AS path. Therefore, you'll know that that particular route came from that.
Right. You can see each hop that internally that your route propagated through, which for debugging is quite nice. Basically, just to give you an overview of what confederations are and how confederations work, BGP allows for three types of peering relationships between BGP-speaking routers. You can have iBGP, which is generally used in either route reflector or full iBGP mesh. You have eBGP, which we all use for external peering or transit. And you can have Confederation eBGP. It's an iBGP with an eBGP look. It has its own kind of unique set of rules. It lets you use some of the cooler features about eBGP, but preserve some stuff. Next hop, local preference and meds are preserved in Confederation eBGP, and Confederation elements in the AS path are not counted for route selection purposes. So that means, and a lot of people have asked this question, let's say you have a route that passes through 10 different Confederation sub-ASs. Is that less desirable than a route that passes through 5 Confederation sub-ASs? And the answer is no, that those Confederation sub-ASs, those member autonomous systems, do not count for AS path selection. Okay. Confederations allow groups of routers to form sub-autonomous systems to eliminate scaling problems with full mesh iBGP. All routers within the sub-AS must be fully meshed or in a route reflector confederation. And what we mean there is that let's say you have one confederation per POP. You're fine in the confederation setup for all of your POPs, but when you look inside the POP, of course you still have to have some kind of iBGP relationship between all the BGP speakers actually in that POP. And it's up to you whether you want to do a full mesh or route reflectors. Confederations are most advantageous when there are fewer routers per sub-AS number. There is no reason to limit the number of sub-ASs you have. Nothing is gained. Our confederation design started with 2 sub-AS numbers. Because we said, okay, we'll do the east and we'll do the west. And we had maybe 30, 40 POPs in each half of the country. The problem is that this doesn't offer a lot of advantages over full mesh iBGP. You just have 2 smaller full meshes. But we found that the more sub-ASs you add, the greater the advantage you got in all of the things we talked about earlier, like survivability, flexibility, and ease of configuration. So when we finally boiled it down, what we got to at the end was having 1 sub-AS number per POP. Each POP would be its own island in a sea of a confederation. And of course, the upper limit on this is 1,000 sub-autonomous systems per RFC. And of course, you won't see in an RFC that it says you can only have 1,000 members of a confederation. What it does say is that there's only 1,000 eligible private AS numbers. Some of the advantages of a confederation of POPs, which is sort of what we're talking about here, is the routers within each POP need only peer with each other utilizing iBGP. You don't need to peer with routers in other POPs. Neighboring POPs are peered via POP border routers, speaking Confederation eBGP. Next hop, local preference and meds are preserved. It's far more scalable than a route reflector environment, and it's also, more survivable than a route reflector environment, and more scalable than full mesh iBGP. How to make it work? Now here's the problem. A lot of people rush into confederations, and they realize when they're through, they didn't get the kind of advantages, they didn't get the kind of output they wanted for the effort they put into it. Now, so at the beginning of our effort, we said, how do we make it work? What do we need to do, planning-wise, to make this efficient? Thoughtful use of sub-AS numbers. We designed a regional approach to make sure we had enough sub-AS numbers assigned and allocated to support our future POP growth. Local preference hierarchy. Useful and descriptive community strings. Meaningful meds, multi-exit discriminators. Use of various policies, access lists, community lists, distribute lists, etc. as building blocks, and the use of peer groups on the Cisco platform whenever we could possibly do it to kind of cut down on some of the legwork. As we said before, sub-AS has become a useful tool for debugging as in show IPBGP on the Cisco platform and show route on the Juniper platform. The suggested assignment of sub-ASs, as we'll show you in a moment, is geographical. Always remember to keep room for expansion and put plenty of extra sub-ASs in your configs. Don't count on adding them later. And the thing to remember here is, on every router that's going to participate in a member AS of a confederation, you have to initially specify all the sub-autonomous systems that you plan on using. So, okay. The way we decided to do our geographical regional assignment was, basically within the U.S., Southeast, Northeast, North Central, South Central, Western, pretty big chunk for Canada, Latin and South America, Europe, Asian, and a reserve block. Now, one reason we put a reserve block in there was because of some of the thoughts perhaps about using BGP VPNs in an MPLS environment. So we wanted to make sure we had a set-aside block in case those sort of VPNs and RFC 2547, really came to the forefront. Here's some sample community assignments for, a small network of POPs. As you can see here, Atlanta has its own sub-AS number, Dallas, Los Angeles, Phoenix, etc. Community strings are the key here. Community strings help this to scale. Communities, for those unfamiliar, are like tags. Can you go back to that slide? They're like tags or post-it notes attached to the routes to help identify them. You can have essentially as many communities as you want, although there are some limits based on implementation, on a route as you want. So if you want 5 or 10 community strings assigned to a route, you can do it. As you said, there can be more than one community string attached to a route. Communities are recommended to be set at the ingress point. You can set communities wherever you want, but to get the most flexibility in your routing architecture, the best thing to do is when your routes come into your network, via peering, via transit, via customer connection, set the communities at the ingress. Communities need to be applied only once, and they cause the administrative burden and complexity of your network architecture to go down significantly. When routes leave your network, filtering can be based on one or more community strings. And what we're talking about here, some sample communities, are regional communities based, again, on where the route entered your network, communities set by peer, customer, internal routes, peering routes, or transit routes. And we'll give you a brief demonstration of how communities are set at the ingress. Okay. Basically, these are some internal routes. We're using 4355, that's the old MindSpring AS number. Basically, we're going to say that one of these routes, 2769/16, is going to be a green route. We're going to call this community that we're just picking green. We're going to say this other network, the 199 network, is going to be a red community. Okay. These are some transit routes that we're getting in from UUNet. Basically, we're going to make these transit routes blue. We'll call that community blue. So you can see in our little routing table here that these two routes, this one is green, red, and 2 blue routes. Now, if we have a customer over here, this is the Earthlink network, let's say we only wanted to send the blue and the green networks out. So we simply use a route map in the Cisco parlance. We filter on communities, and so we make sure that this red route is never propagated. So as you saw here, going back one, as you saw here, basically what we did was we assigned routes on ingress, and we filtered based on routes at egress. Works very nicely. So some of the communities we finally settled on in this structure were customer routes, private peering, transit, and public peering. And of course, not all of these are applicable to all the ISPs we're talking about here, but we tried to be general. For internal routes, we made 2 distinctions. We talked about internal routes that we wanted to be globally visible, and we talked about internal routes that we wanted to be visible to our OPN networks. Now, in MindSpring, we had a number of networks that were OPN providers to us, other providers' networks. We used their dial-up services and we privately peered with them. And there were some circumstances where we wanted to restrict certain services to only our customers and not let the rest of the world see them. stuff like, outgoing SMTP, news, our radius servers. We wanted those announced only to ourselves and to our OPNs alone. So, kind of a protection against abuse of the services by non-customers. And with communities, we were allowed to tag certain routes for export out to those OPN providers alone. Okay. Another thing we assigned communities based on were field versus exchange point peering. In other words, if we're going to privately peer with someone in Tulsa, Oklahoma, they'd get this community. If we were going to peer with someone at a May or a NAP, they would get this community. And of course, we did it based on DC, Atlanta, which was our headquarters. It's currently NetRail's headquarters. Chicago, Palo Alto, Dallas, some of the major peering points. Furthermore, there's some special communities we wanted to build in the support for. No export, of course, and no advertise are both well-known BGP communities, so we built in support. Prefer me and avoid me are proposed well-known communities. We wanted to build in support for that as well. Finally, what we would do is we'd add a community string to represent the origin AS number. For example, for a route that came from UUNet, we'd tag it like this, 4006701. If a route came from Sprint, we'd put 1239 on it. That would help us do some filtering later in case a customer wanted a special load of routes. In other words, they wanted all routes except maybe UUNet routes. For local preference, let's go through this here. Basically, we wanted to have different local preferences for our customers, for peering and for transit. So let's say a customer of ours is advertising 165.200.124 into our network. Now, we're always going to prefer customers, right? Generally in the kind of local preference hierarchy. Customers, then transit, then peering. The reason why is because obviously a customer comes first, then we're generally going to use transit, then we're going to use peering last. And we use transit first because we're paying for it. So local pref of 100 we're going to set for the customer route. Okay, local pref of 100 for the customer route. Then for our
for peering routes, we start to use, we set it to 90 as a second preferred route, just because if it's private peering is usually free, you don't have to pay for it.
Right.
So we want to use up that bandwidth first, or that pipe, rather than our transit route we should pay for.
Right. And when I spoke a minute ago about preferring transit over peering, we're talking about transit over public peering. In this case, with 4006, with a local pref of 90, we're talking about public peering. Finally, we go to transit with a local preference of 60, and we'll throw that in our routing table. So you can see there, we have three possible ways to get to 165.200.1/24. The way that's going to be preferred is always going to be our customer route. And you may say, well, that was going to be preferred anyways. Look at the AS path. Well, that's not always so simple. What happens if the customer starts prepending greatly? We want to ensure that the customer is always going to be routed through our connection to the customer. Okay. Again, in local preference, the higher the local preference, the more desirable the route. Customers always come first. We never want to send their traffic to a peer. Private peering is more desirable than public peering. Transit is less desirable than private peering for economic reasons. So here's the local preference hierarchy we decided on. Always preferred and never preferred correspond to the proposed well-known communities we talked about before. We have two choices for customer routes. Customer routes and customer backup routes. Since some customers want to send backup routes as opposed to the kind of strategy of sending less specific aggregates. Private peering is then preferred. Finally, by somewhat congested private peering, we thought we wanted to put in a step to help us decongest some of the more congested peering points. Paid transit, congested paid transit. Then we get into public peering here with the ATM naps preferred over the FIDI naps. And I presume the stuff like PACs, Ethernet naps would be somewhere in here. So, some of the peer types in our design were local sub-AS peers. By that we mean BGP peers within a POP, Confederation peers, who we're talking about other POPs in our network, transit peers. These are folks you might buy transit from, public or private peers, and customer peers. Okay, for local subautonomous system peers, all peers within a POP are members of this group. The update source for these BGP sessions is the loopback address of the router. You have to recognize communities, and you have the option in these guys to use either full mesh or route reflectors. Remember, this is inside your POP. So basically, routers use the loopback address as the source for your BGP packets. That way, many times inside our POPs, we have multiple gig Ethernet, multiple OC12, multiple OC48 connections between various pieces of equipment. This way we ensure that only one session needs to be created, even though you have multiple paths between these routers. And peering between the loopback addresses, of course, increases your stability because you don't have to worry about a specific interface going down. Confederation peers are all peers that are POP border routers. Basically, if you have one POP touching another POP logically in your network, those guys are going to be the Confederation peers. The update source for these BGP sessions is the facing interface of the router. In other words, we actually want to use the interface IP addresses here. Inbound soft reconfiguration is not necessary. We generally use outbound soft reconfiguration. You have to recognize communities, and of course filtering is done on egress. Meds are set on ingress. We'll tell you what we mean by that in a sec. Basically, here's why we like soft reconfiguration. Of course, clear IP BGP is somewhat hostile to your network stability. Soft out, which is what we like to use here, is a low CPU. That's a good thing. It issues withdrawals for all advertised routes. It recomputes and then resends the routes. We did not want to use soft in when we can control both peers, because essentially we have to reevaluate all the routes received from peers stored in memory, high memory requirements, because we need to store that separately. So we burn up a lot of memory on the routers.
Remember, this is for Confederation peers. In other words, we own both routers.
Right.
It's not necessary to actually use up the memory for the BGP tables.
Right. Here's our config. Basically, what we do is, most of this is pretty straightforward. We use a peer group here where we can. We have two route maps operationally here. The inbound route map, the received routes, sets an additive med. Now, a lot of you guys know meds, multi-exit discriminators. We're using meds in a slightly different way here. We're using meds as an actual routing metric. So what we do, and this is legal Cisco syntax, is when routes come in, we add a certain additional metric to their med. And we use that as a way of determining routing. So that could be set metric plus 100 or set metric plus 200, which of course increments the med. It's also perfectly legal if you wanted to do something like set metric minus 200. It can be plus or minus. Now when we send routes out, we want to do a little filtering. This is even between our Confederation peers. Basically we want to send everything except no advertised routes. And of course no advertised routes are not going to leave the Confederation. So between our Confederation peers, we're not going to send no advertised routes. Routes marked with that no advertised well-known community. We are going to send customer routes, routes we learned from our peers, routes we learned from transit providers, and any internal routes that we've produced within our autonomous system. Now, going back to the whys of the additive meds. Those additive meds we were talking about, those additive meds we're generating allow a tiebreaker based on optimum routing. It also allows an alternative method to de-prefer routes in case of transit or congestion. What we're talking about is basically you can have many situations where you have the same local pref. So let's say it's all peering. Let's say you peer with someone in 4 points. So the local pref is going to be the same. The AES path length is going to be the same. But let's say you want to try to balance that outbound a little bit, balance it in some kind of meaningful way. Well, we can set these meds based on, say, mileage or based on delay in milliseconds. So we can say, okay, send that traffic to the nearest peer rather than just either randomly chosen or the peer with the lowest router ID. That way it can help us to balance our outbound traffic a little bit, hopefully pleasing our peers and pleasing ourselves because we're not overusing a WAN link or a WAN connection. This is currently supported by Cisco iOS. I've made a feature request to Juniper, Riverstone, and Foundry for this feature, so hopefully pretty soon. This is a little example of additive MEDS in action. What we've got here is we have a route 207.69.00/16 that originates in Atlanta. As it traverses the network, let's say our additive MED here is 120, so we have set metric plus 120. So by the time it gets to Birmingham, the MED is 120, and our AS path has 6500, which is its origin over here. By the time it gets over to Dallas, because of this 580 MED, the total MED is now 700, and you can see our AS path, 65,000 and 65,012. You can see why it helps in debugging to have this, because you can instantly see what path the route traversed when you do your debugging commands. By the time it gets to Houston over here, we have two possibilities. One possibility would be this 700 plus 40, which would be 740. The other possibility is 120 plus 600, which is the route we choose and install on our routing table for 720. And as we can see here, 65012, 6500, the more preferred route traversed this way. The less preferred route, 6500, 6512, and 65400 traverse the long way. So we got an optimal routing choice here.
I have a question.
Yes.
Within an IGP, is the number of sub-AS numbers counted in determining metric, or?
Within an IGP?
I mean, within your
It's not. Basically, this doesn't affect the routing choice. When you're doing an AS path length by RFC, this equals 0. This also equals 0. This equals 0, etc. So it does not come into play.
Got a question for you?
Certainly.
The assumption here is you're not underlying all this BGP infrastructure is not one IGP.
You don't need to. That's part of the assumption. You can underlie it with an IGP. It works if you underlie it with an IGP. However, there are a couple of other approaches that work. Between these POPs, you don't have to run any kind of IGP between them. You can simply have, say, OSPF running in area 0 here, and OSPF running in area 0 inside this POP as well, and they never have to talk. This turns BGP into a really cool IGP as well.
I was just curious, in terms of operational experience, how is the reconvergence in comparison if everything was just?
It's pretty good. It's fairly impressive. Of course, you want to turn dampening off. That's a big thing. When we were doing some early operational tests of this, dampening was on and we couldn't figure out why things were unreachable. You do a show IP BGP dampening and you're like, whoa, I've dampened half my POPs out. So you don't want to be dampening your own routes if, say, one of the interfaces inside your network flaps for some reason, because then you could essentially black hole one of your POPs. But the convergence time here we found was very favorable. And the other thing that's cool about the convergence time is it's as good as OSPF, and the other nice thing is we don't have to worry about OSPF scaling concerns. That's the other really nice thing. We can keep all of our extra routes outside of OSPF. And at MindSpring, where we had lots and lots of externals, it was very useful. For transit peers, this is somewhat of a different story, because of course for a transit peer, we only control half of the action. We control our router, but we can't control the transit provider's router. So the update source for these BGP sessions is the facing interface address of the router. Soft reconfiguration should be used. Now before we said don't use soft reconfiguration. The reason we use it here is because we have to. It uses a little more memory, but we only have control of one router. Communities must be recognized. Of course, since it's a transit peer, we're only going to send out customer and internal routes. We're not going to send out peer routes, for example. We're going to apply an import ACL that prevents reception of Martian routes. Of course, that's only necessary on a Cisco. On a Juniper platform, there's automatic filtering of Martians. We're also going to assign proper communities and local preferences. We're also going to allow prepending certain subsets of routes with additional AS numbers for AS path length prepending. Here's a sample config. This is going to be posted on the web if you want to look at this a little more closely. Most of this should be pretty familiar. soft reconfiguration, a distribute list for Martians. We have a route map in and a route map out. Now, basically, what we're going to do for that is the route map in is going to set our community strings up, and this might be, say, a regional community string. It might say that it's in the field, it's field peering, for example, or field transit, and it might say that this is a transit connection. So with 3 or 4 community strings, we triangulate. We can really get pretty granular, and we can say that's a transit connection. It's not in one of our major hub cities, and it's in the southeast, for example. So it gives us a lot of data to use. We also are going to set a community that's going to correspond to the AS number that we're getting transit from. We can also, over here, as you see, when we send stuff out, if we want to, we can do AS path prepends. So some of the AS path filters you saw before were just stuff not to send out, no exports, no advertised, peers or transit routes. We don't want to turn ourselves into a transit AS for different transit providers. That would, of course, be a bad thing. We do want to send out customer routes and internal routes to our transit providers. There's a couple of transit tricks we ran across while developing this, including depreferring routes for congested outbound. We've used this pretty successfully. This doesn't just work with transit. This can work with peering in some ways. Basically, what we'll do is we'll deprefer routes by setting local pref lower based on AS path length. We'll have an AS path regular expression that will say for path length 1 or 2, set the local pref normally. For, say, AS path length of 3 or greater, deprefer it. Have a lower local preference. What that does is, if you have transit, that'll force that outbound traffic out other transit connections that have a higher local pref for AS path length 3 and greater. That's a very nice way of dealing, even if you don't use Confederations, this is a very nice way of dealing with congested outbound peering or transit. The nice thing about peering and transit there is, let's say you have a congested peering connection and you also have transit. You can use this trick to say, okay, for really advantageous stuff, for the really good routes, we're going to use that peering connection. For the stuff that's kind of, so-so anyways, we're going to send that stuff out to transit and kind of hope it finds its way home. So, let's see. Okay, now for OPNs and setting OPN routes, again, we have some provisions in here, some special communities for folks who use, outsourced dial-up. Lots and lots of us do. So we have some special provisions in here for sending routes out to OPNs. Basically, this is our section on public and private peers. Again, the update source for these BGP sessions is the facing interface, soft reconfiguration. All of this should be very familiar because it's just like transit. And again, here we have the option, as we said before, to use local preference to force everything to that peer that should go to the peer, or we can deprefer and shift some outbound to transit providers. This is again very similar. Again, the main difference here is we're only going to send customer routes out. There's a slightly different route map that's going to say this is a peering connection rather than this being a transit connection. Again, we're going to send out only customer and internal routes and none of these other routes that we don't want to send out. Customer peers are a little bit different. This is where it gets interesting. All this stuff is the same. Again, we only control one side of the relationship here. Communities must be recognized. Now, this includes communities sent from the customers. Part of the idea of this setup is that our customers can send to some of these communities and set their own local preference, that kind of thing. In other words, if they want these routes to be backup routes and these routes to be primary routes, they can send us communities to that effect. We can send only selected routes based on customer requests. That way, if they want to make sure that UUNet traffic gets to UUNet and doesn't go through our autonomous system for some reason, like some significant prepending at some point, they can make sure that we can say, okay, we're only going to send you the whole internet routing table minus Sprint or minus UUNet, for example. Again, we're going to apply ACLs to prevent Martians. And also, we're going to apply import filters that only accept specific customer routes. Now, that's different from what we did with our transit providers and our peering partners. We essentially accepted anything they were going to give us. Here, we are going to put some import filters on, and we recommend using RTconfig to query route arbiter database and automatically generate the access control list. Now this will be pretty familiar to those of us who work for ISPs that offer dedicated service of any kind. There's a couple kind of routes we can send. We can send full routes, which are generally customers, peers, internals, transit. That's what we call a full view. Right now, a full view is about 79,000 routes. We can send customer routes. Customer routes are generally customer and internal routes. It's good for some of the weaker Cisco routers. You know, Joe Blow has a 2620 or something in his POP. I was about to say 2501, but I don't think 2501s can even handle customer routes for most folks these days. They're just too weak. This is what's called a partial view. As routers have become more powerful, the number of times you get asked for a partial view these days is getting much, much rarer, especially when you can put like a Cisco 3640 in a POP. It's pretty inexpensive. It'll take a full view. Finally, the third classical choice has been for default routes. Generally, we'll send only quad 0/0 pointed to the router interface. This is of limited utility. If you have multiple providers sending you this, you're just doing, okay, that's going to you, that's going to you, that's going to you. There's no intelligent routing going on there. So we don't get a lot of requests for that. Special considerations for customers: carefully filter routes. The farther downstream you get, generally the less clueless you get. Filtering can be based on AS path or prefix. We recommend filtering by IP access list, in other words by prefix, using route arbiter database tools if possible. We feel that using AS numbers to filter is kind of like playing with fire, especially with some of the sophistication level of some of the folks we're running BGP with these days. Customers do not have to advertise the same routes everywhere. Peers do. That's one of the biggest misapprehensions we run into. We talk to a NOC guy or something, they're telling a customer, hey, you have to advertise the same routes everywhere. No, customers can do whatever they want to. They can advertise little tiny pieces of routes. They can advertise big blocks. They can advertise different things in different POPs. Peers have to advertise the same thing everywhere. Customers don't. Now, that isn't to say that we're going to guarantee that any block they advertise is going to be globally routable. We won't do that. And we'll tell them we don't want them to advertise, say, a /29. We're not going to propagate that. But if they have a /18 and they want to carve that up into /22s, and they want to do them in different POPs, because let's say they don't have a WAN backing up behind that, they want to run isolated eBGP, we're going to let them do it. Basically, for customer configuration for full routes, we'll run through these pretty quick. These are pretty similar. There's an import filter. As you notice, we switched to Junos. We're equal opportunity offenders here. We ragged on iOS long enough, so now it's Junos' turn for a little dose of the punishment. Basically, there's can you go back one? Basically, there's no export filter. We're giving them all the routes we got. We have an import filter. The convention we use is the city, like Atlanta, then my code would be my company. We're going to accept these two routes, and only those two routes. Of course, this could be automatically generated pretty easily from RT-config. Here, this is what we're accepting from them: customer name -in. We set a local preference, community strings, etc. And on a Juniper here, it's much easier to see. This is a customer. This is not at an exchange point. This is in Atlanta, and that's the customer name. So the communities are much more obvious. Partial routes is exactly the same. The only difference is we're only exporting customer routes. In other words, we're saying, we're not going to send out no export and no advertise routes, and the only ones we're going to send out are going to be internal routes, customer routes, and customer backup routes. We're not going to send out routes we got from peers or anything like that. Finally, default route only. I think this has kind of fallen out of favor in the general internet community. Cisco still supports it with their default -originate command. On the Juniper, it's a little more complex. You have to kind of build a default route for the customer and shoot it out to them. The way you do that is, this looks pretty standard. This is a pretty standard customer BGP peer group, but we have an export policy statement called default originate, which we just made up. And basically what we're doing is we have to insert we only have to do this part once. We make a static route, and most of us run defaultless networks, but we have to put one in and then not install it as a route. Can you go back one? And then not install it as a route. We make the next hop the loopback address of our router. Then as we export it, we take that route, We're activating it as we do this. We set the next hop self. In other words, we make the next hop all router interface. We accept it, it goes out. So there we've just invented default originate on the Juniper. We don't think people are going to have too many, chances to use that. Any questions? We ran through this pretty quick, so if anybody has any questions, we can go back, talk about this stuff. Seem to make sense?
Are you using additive communities or
Additive communities. But of course, it's not really an issue because, we're only adding communities at ingress. But of course, if we just strip communities and didn't do additive communities, we'd lose the communities our customers are sending us. And that we don't want to do. We want to keep the communities that our customers send us. We don't currently. So, maybe if sometime we all get together and reach a standard on some kind of community signaling, some kind of reserve communities we can use to send us the secret lodge sign between ISPs, that might be useful. But right now, we don't see a huge, great utility. That kind of lends itself to sort of one-off solutions between individual peers, and we really wanted to standardize. We made a document behind this. This presentation is pretty shallow, but the document behind this is about 50 pages, and we're going to publish it to the web as soon as we put the finishing touches on. We already did one large-scale deployment of this on the classic MindSpring network that's now owned by Earthlink. Within the next 60, 90 days, there'll be a large-scale deployment on the NetRail network as soon as the Junipers go in. When that happens, when we have two, large full-scale deployments, we'll publish the paper, and you'll be able to see kind of the depth that went into it and the effort we made to standardize the approach.
It's kind of interesting too, since the two networks are quite different as far as the focus is concerned. Earthlink is more towards a dial-up network, heading towards individual residential customers, whereas NetRail, we're more towards catering towards ISPs as their customers. Therefore, the knobs and the bells and whistles are kind of different for each network. So it's kind of interesting too.
Right. We felt if we couldn't find two networks that were much more different than MindSpring and NetRail. So if it works for MindSpring, it works for NetRail, it should work for anybody. Other questions?
Getting back to my earlier question, do you feel that with this type of design, your sub-ASs should be relatively well matched and not having to transit through many sub-ASs before you actually address Confederations?
Well, we really don't see a huge utility for pardon me. We don't see a huge utility for that. We don't feel it really matters much one way or the other. In the NetRail network, what we're going to do is, in our major hub cities, we're putting in optical switches eventually, which are going to fully mesh up the hub peering cities. But the other cities, the satellite cities, the Albuquerques, for example, are still going to be kind of on the string of pearls. They're still going to be out there, so you'll still have to do a certain amount of transit through the sub-ASs. But
let's say hanging on strings
right.
of pearls, and a link between two very remote sub-ASs goes down. It gets back to I was kind of surprised that if I'm, multiple sub-ASs away, I'm going to learn about that failure just as quickly in BGP updates as I would have from an IP.
Right.
It kind of surprised me. Especially if I can see if I'm, if the two ASs that are directly connected off the same physical link, they can repoint their next hops pretty quickly. But if I'm 4 AS hops away, it just seems surprising that I'm going to potentially find out about that link going down as quickly in BGP as I would.
It really works remarkably well, and the only thing we could say is try it. We had great success with it. Neither of these networks is huge. None of these is UUNet. Our convergence time was always, measured in a matter of seconds on both of these networks. So if it was 0.25 seconds one way or the other, chances are we never would have noticed. If this was AT&T, we probably would have done a little more testing in that area. So, Philip.
Not as American network.
Well, that's...
Right.
Can you stand up and repeat that?
Sorry. One user says, well, that's what we're going to insist on peers announcing the same route vehicle once and it's so blind.
The design doesn't actually insist on it. Simply most of our peers do. They want to make sure that traffic is essentially balanced across peering connections. So, kind of in the interest of fairness, that way, what's the best way to describe this, Miguel? I mean, it's simply more of a fairness issue for the peers to ensure that routes aren't going to get, have to traverse the peers network in an inordinate amount. It's a fairness issue to make sure it's going to traverse our network in equal amount.
So that you don't have to pay the transit costs to send traffic back to the customer.
Yeah, at some point, it makes sense, economic sense to actually use your peering connections. At some point, it might be more cost-effective to send it out with transit links. It really depends. For example, if you had a peering connection, you only had one peering connection with company A in New York, and you get its routes. I mean, you may or may not want to propagate its routes all the way to Seattle and traverse your backbone, because it might be more cost-effective to just send it out through a Seattle transit. There are cases wherein that's true, in which case we may decide to just restrict the passing of the peering routes within, or keeping it within a region. That's
one of the things the community structure lets us do, is restrict routes in a regional manner. But to go back to Philip's question, let's say you had a peer in New York and a peer in Los Angeles. Let's say that they were announcing different routes out those different peering connections. Let's say they were announcing all of their routes out in LA and only some in New York. Let's say in your New York POP, you had some traffic for them, but it's not one of the routes that's being announced to you in that specific location. Well, on your dime, on my dime, I have to send that traffic all the way across the country to LA in order for it to get into the other person's network and then go into them. And that's not really the point of peering. I shouldn't have to pay to send that outbound traffic all the way across my network. Generally, the deal with outbound is, we can dump it off at the closest point, and that the person on the other side pays the long-haul costs involved. That's one reason why inbound is considered to be so much more desirable, because inbound traffic is going to traverse the other guy's network, and it's not going to be traversing across your network.
You might have a common set of routes at both points, but the other routes will generally be disjoint subsets. I'd have to argue that you might want to carry them across your network.
I can see situations where you might. The reason we put it into the presentation this way is because this is essentially just what they do in America for peering. There are arguments you can make one way or the other, but we wanted to put it in there because that's what was standard and that's what was expected of peers. It's expected of peers that you announce your routes the same at every peering connection. So, other questions? I haven't thought about that but basically the question was, there was a lot of feedback at the last NANOG. There was a presentation about prefer me and avoid me. There were some security concerns. We didn't put a lot of time into thinking about those particular concerns. On the MindSpring network, it was a pretty minor issue. With NetRail, it may be a little bit more of an issue in that someone could use it to I guess, induce supremely suboptimal routing in someone else's net blocks. But no, I have to say that hasn't really been an issue we've considered.
Do you send prefer me and avoid me outside the network?
No, we don't. So we have not. It was kind of going to be used as an internal thing. As you can see, we didn't really implement it much, but one of the efforts we made in this process was that we only really wanted to do this once, so we wanted to put as many hooks in as possible, as many different possibilities as we possibly could. That way we get greater flexibility. But we don't anticipate a huge need for prefer me and avoid me in this context. So, other questions? Philip?
Come back to international networks again. You take these constraints for your defining communities. private brand. Internationally, it's kind of accepted that you use the country dialing codes as part of the community in order to provide meaningful community.
Really?
But unfortunately, you just tag all of your inbound answers and theory with more than 65,000. So you just lost the ability to do that.
No, I don't think we did actually. Remember, there's a difference here between the BGP sub-AS numbers and the communities. So you're kind of juxtaposing the two. We can put whatever community strings we want on the routes. When we put 65,000 on there, that's not a community string. That's a Confederation sub-AS number.
But you're using community strings of like 65,010 to indicate that it was initiated in May East or whatever you received in May East.
Right. Well, for this particular, I guess you're right in that sense. No, we've put 65,000 as the community string also, because we wanted to be able to use the AS numbers of our transit or peers as part of the community. For example, if it was 406 and 01 would be meaning it was a route received from UnionNet. But you did bring up an interesting point there for the use of the area codes.
Yeah, so something to keep in mind is neither of our companies has a huge international strategy, which probably was portrayed in this sort of thing. So, but yeah, we can put that in. That's actually a fascinating point, country codes. So we'll take that away.
You are working on the international community strings, our idea for it. I'd love it if you could promise you to try it, but I won't be shocked at these things.
Sure, that sounds good. We won't tell anyone at Cable and Wireless who sent it. So, any other questions? Comments? Yes.
Are you using this additive net technique throughout the network? Are you running any IGP at all? Or
Right now,
additive net?
no. Right now, we're using it on top of OSPF. So we still do have a backbone, an area 0 throughout our network, but we're moving towards having that separate or isolated area 0 for top. We haven't gotten there.
Yeah, just got to fix on a scaling issue.
So aren't you, if you're going to use the additive net technique, so that would be the only method you have, are you zeroing out the net being received?
Yes, that was actually on there. Yeah.
So you can actually do that.
You're ignoring the hints that your peers give you, that you don't trust those hints anyway to zero.
You bet. We're doing that, and the reason we're doing that is because from some of our biggest peers, some peering points, we get meds, and some peering points for the exact same routes, we don't get any meds. So until folks can kind of put their heads together and figure out a good way of looking at meds, now we do listen for meds from our customers. And that's the difference, because we can call our customer and say, hey, you're doing something weird. So it's a leverage thing. It's a layer 8 kind of issue. So
you mentioned when you were analyzing self-vectors versus confederations, one of the advantages of confederations was, or one of the drawbacks of vectors was the need to configure all customer drivers separately. If I understood correctly?
no. No, it really didn't have anything to do with customer routers. We felt the drawbacks to our route reflectors is they work best on an ATM network, fully meshed. And we felt there was the possibility of isolating POPs from route reflector servers.
I mean, even with this setup, yes, you still need to set up your access list filters per peer. So, I mean, it really isn't that much of a big difference between the route reflectors and Confederation. That was just my thought.
Right.
Yeah.
Sure. As far as customers, it's the same.
It was more towards the fear of isolation.
Right. It was a survivability issue when you don't have ATM to do redirects. When you have a packet over SONET network, there's no rerouting going on there necessarily. So we wanted to do something that would be very, very survivable.
When you were talking about the optical switching and resilience for the network,
Right.
Are you advocating using head drop technology in that?
I have to admit that I'm not a huge optical guy, so I can't fully address that. My director of optical transport engineering, though, tells me wonderful things about optical switches that we can use in some of the same manner that folks used ATM switches for, to essentially make it look like we have a full mesh in certain cities. Now, our plan was not to deploy those everywhere, mostly because of the intense cost of that kind of hardware. We were just going to deploy it, say, in our hub peering cities, so it would look like there was a full mesh between the hub peering cities, even though, of course, we don't have the fiber route miles between them. But because of the high cost, we still need something like the Confederation approach to go for, the 80 pops that aren't in the hub cities.
I guess the big debate these days whether or not that you ought to use a protected mode ADM interface off the network computer, or you should just take the ladder straight out, drop it straight into a route, and let the layer 3 technology.
The nice thing about this approach is that it works either way. We don't lose anything if we have the optical switches. We don't gain anything if we don't have them. It's pretty much a wash. It maybe improves the stability of it a little bit if we have that kind of reroute capability. But in this kind of approach, layer 3 handles it just fine. And when layer 1 kind of catches up with that neat technology, we'll still be okay. So, other questions?
Do you have any method to support customers who request meds from you? Say a customer has their own network, international network, and they want meds, so they can do like that,
They'll get meds.
So how do you do that with Confederation?
Same as you would do with any other kind of BG.
Well, let's say you have a prefix that's in the West Coast, that's what prefix, that's what
Mm-hmm.
and the customer's currently from both coasts.
Right.
Prefix.
We wouldn't actually set the med per se. The med is going to be set through the additive med kind of scheme. So they're going to see that med. Now, if they want to, so that's basically what's going on. If they want to inject routes into our network of different meds, we can. Yeah, they're going to get them based on this. They'll see our meds, and they'll be meaningful meds because they'll be based on delay or mileage or stuff like that. So the meds will actually be useful for them, we hope. Other questions? Comments? Summary. Okay. Well, let me just summarize real quick where we're at here. Basically, what we feel this kind of Confederation approach gives us a number of key benefits. One of those is less complexity. That was a big one for us. Greater stability, more flexibility for traffic management with those additive meds, greater survivability with the POP as Confederation approach, lower engineering and administrative costs, mostly thanks to our community structure. We have fewer ranks of guys typing in filter lists and AS path lists, increased uptime, going back to the greater survivability, and we feel this is going to let us build, at both of our networks, a scalable next generation IP network. Any final questions? Well, thank you guys for coming out tonight. We appreciate it.